Hello, today I'm going to work through a set of questions that you might typically get in an AS level physics exam on electricity. The key formulae that we're going to use is I equals Q over T, that is to say the current is the amount of charge conveyed in a particular time. I equals NAVQ, which tells you about the amount of current depending on the number of charge carriers and their velocity. V equals W over Q, that is the voltage is the work done divided by the charge. R is rho L over A, that's the resistance, is the resistivity times the length divided by the area of a wire. V equals IR, that's Ohm's law. P, the power, is voltage times current. The voltage in a circuit will be the EMF of the battery minus IR, which is the current in the circuit times the internal resistance of the battery. The period of an oscillation is 1 divided by the frequency, and we'll need that for AC. VRMS, the root mean square of voltage, is the maximum voltage divided by the square root of 2. The IRMS, the root mean square current, is the maximum current divided by square root of 2. And in the case of AC, power is equal to the root mean square of the voltage multiplied by the root mean square of the current. Question 1. A battery supplies 5,400 coulombs in 15 minutes. What is the average current? So here we need the formula that I is equal to Q over T. Q is the charge in coulombs, T is the time in seconds. And that is going to be 5,400, because we said it was 5,400 coulombs, divided by 15 minutes. Well, 15 minutes in seconds is 900 seconds, and that gives you a current of 6 amps. Question 2, we are asked to find the drift velocity of electrons flowing through a copper wire, and the information we are given is that copper has 10 to the 29 free electrons per cubic metre. We know that the cross-sectional area of the wire is 6 times 10 to the minus 6 metres. The current flowing through the wire is 10 amps, and the charge on an electron is 1.6 times 10 to the minus 19 coulombs. The formula we're going to need is the one that says that the current is equal to the number of charge carriers times the cross-sectional area times the drift velocity times the charge on each carrier. And that means that V, which is the drift velocity that we need to find, is going to be I divided by NAQ. Well, we know that the current is 10 amps. We know that the number of free electrons is 10 to the 29 per cubic metre. We know that the area is 6 times 10 to the minus 6. And we know that the charge on the electron is 1.6 times 10 to the minus 19. And in circumstances like this, the most difficult thing is to keep track of all the 10 to the minus 6s and 10 to the minus 19s. But if I've got it right, that should be 1.04 times 10 to the minus 4 metres per second. So in fact, the drift velocity of electrons through the copper wire is very, very slow. It is something of the order of 1 millimetre per second. Question 3. We have a 10-volt motor, and we are asked what is the charge that will be required if that motor is to do 100 joules of work. For this we need the formula that voltage is work done divided by the charge, and that gives us that work is equal to the voltage times the charge, and the voltage is 10, and we say that we want 100 joules of work, and we want to know what is the charge, and obviously the charge Q is going to be 10. 10 times 10 is 100. So we need 10 coulombs of charge for a 10 volt motor to be able to do 100 joules worth of work. Now the second part of the question is, suppose that motor engine is only 80% efficient. What charge do you now need? And the answer is that the charge will be the 10 volts divided by the 10 coulombs, which was the answer we got here, divided by 0.8 because it's only 80% efficient. And that gives you 12.5 coulombs. You need a higher charge if there's a lower efficiency because some of the work is wasted. That's the whole point about efficiency. If it's less than 100%, you lose energy. And consequently, you needed a higher charge because 20% of that is going to be wasted. And that will leave you the remainder that will generate actual work in the motor. Question 5. We're asked to calculate the resistance of a wire. And I can tell you that the resistivity of that wire is 2.8 times 10 to the minus 8 ohm meters. I can tell you that the wire itself is 4 meters long. I can tell you that the diameter of the wire is 1 millimeter. So we're going to need the formula that resistance is rho L divided by A, which is 2.8 times 10 to the minus 8 times the length, which is 4 meters, divided by the area, which is going to be pi r squared. R, since the diameter is 1 millimeter, I think R will be expressed in meters, 0.0005 meters, and that's squared. And that should give you a resistance of 1.78 times 10 to the minus 1 ohms. The second part of the question is, what happens if that wire is cooled below the transition temperature for copper, which is 1.2 degree Kelvin? What happens if it goes below that temperature? The answer is the resistance will fall to 0 because once anything falls below its transition temperature, it becomes a superconductor. Its resistance is 0. A current would flow in that wire forever. Question 5. An experiment is done which generates the following results. Across a resistor, a voltage is measured. When the voltage is 2 volts, the current is 3.33 times 10 to the minus 3. When the voltage is 7 volts, the current is 11.66 times 10 to the minus 3 amps. And when the voltage is 13 volts, the current is 21.66 times 10 to the minus 3 amps. And what we want to know is, what is the resistance and does it obey Ohm's law? Well, first we better check to see if it obeys Ohm's law. And of course we know Ohm's law says that V equals IR, where R is a constant. Consequently, if we do V over I, that will give us resistance. And if you take V divided by I in each of these cases, you should get the same value. And in fact, you do. In each case, you get a value of 600 ohms. And therefore, that particular substance is obeying Ohm's law. Question 6. We have an electric fan heater which is plugged into the mains, which in this country is 230 volts. The electric fan heater consists of 2 parts, the actual heater itself and the motor that drives the fan. I can tell you that the heater is rated at 920 watts and that the motor has a resistance of 200 ohms. And we are asked to identify 4 things. Firstly, what is the current flowing through the motor? Secondly, what is the power in the motor? Thirdly, what is the total power of the entire unit? And fourthly, what is the energy in kilowatt hours in 15 minutes of use of this fan heater? First question, what is the current through the motor? Well, we're going to use Ohm's law, V equals IR, which means that I through the motor is equal to V over R. The voltage across the motor is 230 volts. And the resistance, we've been told, is 200 ohms. And that means that the total current going through the motor is 1.15 amps. The power of the motor is the second thing that we're asked. And power is voltage times current. The voltage is 230 volts. The current through the motor we've just calculated is 1.15, and that comes to 264.5 watts. The third question is, what is the total power of the whole unit, motor plus heater? Well, we know that the power of the heater is 920 watts. And we know that the power of the motor is 264.5 watts. And that gives us a total of 1184.5 watts, which is very roughly 1.2 kilowatts. And then finally we're asked, what is the energy in kilowatt hours in 15 minutes? And energy is power times time. The power, we said, let's just use this simple approximation here, is 1.2 kilowatts. The time was 15 minutes, which is a quarter of an hour. We want it in kilowatt hours, so kilowatts and hours. And that, of course, is going to be 0.3 kilowatt hours. Question 7. A 12-volt car battery delivers a very high current to a starter motor. This is the starter motor. It's a 12-volt battery and it's going to deliver a current of 60 amps. I can tell you that the resistance of the wire that connects the battery to the starter motor is 0.02 ohms. And the question we are asked is, what is the energy that is used to start the car, and what is the energy that's wasted in the wires? Well, first of all, we can find the power. Oh, I should incidentally tell you one further piece of information, which is that it takes 2 seconds for the current to start the motor. So the power is VI, and the energy is power times time. So energy is obviously going to be the voltage times the current times time, and that is the voltage, which is 12, times the current, which is 60, times the time, which is 2, and that comes to 1440 joules. So the battery will deliver 1440 joules of energy to start the car. What is the energy wasted? Well, the energy wasted will be the energy that is wasted in the resistance here, and that's going to be, energy is VIT, but you can also write VI as I squared R times T. And I is 60, so you've got 60 squared, times the resistance of the wire, which is 0.02, again times the time for which the current flows, which is 2 seconds. And that will give you 144 joules. So the battery is delivering 1440 joules to start the engine, but it's actually wasting 144 joules, that's 10%, is being wasted through the wires itself. Question 8. I have a battery, it's a 24 volt, that's its EMF, and it has an internal resistance of 1 ohm. And it is driving an external resistance of 5 ohms. And the question that we are being asked is, what is the current flowing in the circuit? And what is the potential, in other words, the voltage across the resistor? Well, what we can say is that the total voltage is going to be the current into, that's the total EMF, is the current into the external resistance, call that R, plus the internal resistance, little r. And so I is going to be the EMF divided by R plus R. Well, the EMF is 24 volts. The total resistance R plus R is 5 plus 1 is 6, and that is going to give you a current of 4 amps. What then is the voltage across this resistor? Well, that's just Ohm's law. V equals IR. What is the current flowing through that resistor? We've just calculated, it's 4 amps. What is the resistance itself? 5 ohms. And so you've got 4 times 5 is 4 times 5 is 20 volts. So although the EMF is 24 volts for the whole battery, across the resistance there was only 20 volts because you've actually lost 4 volts across the internal resistance of the battery. Question 9. We have an electronic circuit that looks like this. Three resistances. The values of the resistances are 6 ohms, 3 ohms and 4 ohms. And the question is, what is the current that flows here? We'll call that I1. What is the current that flows here? We'll call that I2. And what is the current that flows here? We'll call that I3. So what are those three currents if we have a 12 volt battery driving through those resistance arrangements? Well, the first thing we have to do is to find out what the effective resistance is of these two resistors in parallel. And you'll remember that the formula for that is that 1 over R effective is equal to 1 over 6 plus 1 over 3. In other words, 1 over the effective resistance of the pair is 1 over the first resistance plus 1 over the second resistance. And that's going to be, you can divide both by 6, that's 1 plus 2 over 6, which is 3 over 6. But 3 over 6 is 1 over the R effective. So remember that means that R effective is 2, 6 over 3, which is 2 ohms. So the effective resistance of this little section here is 2 ohms, which means the total resistance in the circuit is 4, plus the effective resistance of this, which is 2, which is a total of 6 ohms. So now we can work out what the current is flowing through the entire circuit. We know that V equals IR, and that means that I is going to be V over R, which is, well, the voltage was 12 volts, and we just calculated that the total effective resistance is 6. So that's 12 divided by 6. That's going to be 2 amps. So 2 amps is coming through the circuit. So that is I1. Now we need to know what is the potential drop across this parallel arrangement here. Well, we know that the effective resistance is 2 ohms. We calculated that. And we know that the current that is flowing is 2 amps. We just calculated that. So the voltage across that pair of resistors, that parallel pair of resistors, is going to be the current flowing, 2 amps, times the resistance, and the effective resistance we calculated was 2 ohms. So it's 2 times 2, which is 4 volts. So there is 4 volts across this arrangement here. So now we can say there's 4 volts across the 6 ohms, and there's 4 volts across the 3 ohms. So in the case of 6 ohms, we can say that V equals IR, V equals I, which is I2, the value we're trying to find. V equals I2 times the value of the resistance, which is 6, and the voltage, of course, we said was 4, so I can cross that out and say 4, and that means that I2 is going to be 4 over 6, which is 0.66 amps. To find I3, which is coming through here, we say that across this whole unit is 4 volts and a 3 ohm resistor. You now have the situation where V equals IR, V is 4, I3 is what we're trying to find, and the resistance was 3, and that means that I3 is equal to 4 over 3, which is equal to 1.33 amps. So now we've found the current through all the 3 currents that we were asked to find, I1, I2, I3. I1 we discovered was 2 amps, I2 was 0.66 amps, and I3 was 1.33 amps. Question 10. I've pre-drawn this. It's the sort of thing you might see. Don't panic, just work steadily through it. We have a circuit here which has 5 resistances or 5 resistors, and I can tell you that they are each of exactly the same value. They are all the same value resistors. And what we are asked to establish, we are told that it's a 12-volt battery, and what we are asked to establish is what is the potential difference across AB, that is across this resistance here. What is the potential difference across AC, which is across this section here? And what is the potential difference across BC? So essentially, if we were to put a voltmeter across AB, across AC, and across BC, what would it read? Well, firstly, let's just take this line here. What is the potential across the entire 2 resistors? Well, it is the battery. The battery comes down to both of these here, so there's 12 volts across these 2 resistors, and they are equal in size. So the potential drop across each resistor will be the same. If the total is 12, you can see that the potential drop across half, or just one of them, will be half of the 12. So the potential drop across AB is going to be 6 volts. Now we need to look at the potential drop across AC. A is just the same as that there. There is no potential difference between these 2 points because we're regarding this as a resistor, a wire that has no resistance. So there's no potential drop here. So A is just as easily considered to be here. Once again, we ask what is the potential drop across the entire 3 resistors? And the answer is it's the battery. 12 volts across all 3 resistors, but all 3 resistors have the same value. So there will be the same potential drop across each of them. And if there's 12 volts across 3, then there must be 4 volts across just one. 4 volts across that one, 4 volts across that one, 4 volts across that one. So how many volts drop between that one and that one? Answer 4 volts against there, 4 volts against there. Total AC is going to be a voltage drop of 8 volts. Now comes the difficult one. What's the voltage drop across BC? Well, let's just think about what the potentials are of these 2 points, B and C. First of all, C. We just said that 12 volts is dropped. Remember, the positive side of the battery is here, so this is at 12 volts and this is at 0 volts. 12, 0. And we said there are 3 equal resistors, so they're each going to drop 4 volts across each resistor. So that means this is 12 volts. This point C, therefore, must be at 8 volts. This point here must be at 4 volts. And this point here must be at 0 volts. Now let's think about this bottom line here. We said 12 volts is dropped across the entire bottom line because it's the battery that's across it. And they are 2 equal resistors. So there's 12 volts being dropped across the whole thing, which means there will be 6 volts dropped across each resistor. So this point is at 12 volts, this point is at 6 volts, this point is at 0 volts. So point B is at 6 volts. Now look, it's easy. This point is at 8 volts, this point is at 6 volts. Consequently, the difference between the two is 2 volts. Question 11. First part, once again I've drawn the diagram. We have a 12 volt battery. It is going through a 30 ohm resistor, a 50 ohm resistor, a 10 ohm resistor, and these terminals are, as it were, open. They're not connected to anything yet. They will be, but for the first part of the question, they are not. And we are simply asked, what is the potential difference across AB? In other words, if you were to put a voltmeter across A and B, what would its reading be? And the thing to remember here is that this 10 ohm resistor is for all purposes irrelevant, because no current is flowing in this wire, because the A and B aren't connected to anything. The only current that flows is the current that's flowing across here. So when you measure the potential difference across AB, you're essentially just measuring the potential difference across this resistance here. And what we can say is that is Ohm's law, of course, V equals IR. For this circuit here, because no current flows here, for this circuit here, we've got voltage is 12 volts, and that equals the current that flows in this circuit times the total resistance, which is 80. And that means, ignore the piece of paper here, I made a mistake when I was doing the calculation, so I thought I'd better start again, that the current is 12 over 80. We're not actually asked to identify what the current is, so I'm not going to waste time calculating that, because all I now need to say is that the potential difference across here, which is the potential difference across the 50 ohms, is simply going to be Ohm's law, V equals IR, so V across AB is equal to I, which is 12 over 80, times the resistance, which is 50, and that, I think, if you calculate it, will be 7.5 volts. Now we come to the second part of the question. We're told that we're going to put a 40 ohm resistance across AB. A 40 ohm resistance is now going to be put across AB. So now a current will flow in this part of the circuit because it's joined up. 40 ohm resistance. Question is, what is the current that flows through the resistance of 40 ohms across AB? Oh, that starts to get a bit more complicated, doesn't it? Well, let's just think about it. We've got a circuit which has got 30 ohms in it, and then we've got essentially a parallel set of resistances. We've got 50 ohms here, and then we've got 10 plus 40, which is 50 ohms in parallel. So this section here really can be thought of as a 50 ohm resistance here and a 50 ohm resistance in parallel here. And the current is therefore flowing down through the 50 ohm resistance here and through the effective 50 ohm resistance here. What is the effective resistance of two resistors in parallel? Well, 1 over R effective is equal to 1 over 50 plus 1 over 50, which of course is 2 over 50, which means that R effective of this little section here is going to be 25 ohms. So now you can say that this entire circuit, which includes a 40 ohm resistance here, is made up of a 30 ohm resistor here and an effective resistance of 25 ohms. So it effectively reduces to 30 ohms and 25 ohms, which is the effective resistance of the three resistors, the 50, the 10 and the 40 across here. And that is being driven by a battery of 12 volts, because that's what we used up here. So now what is the current through that entire circuit? The current is going to be V over R, which is 12 over the total resistance, which is 55. What then is the potential difference across the 25 ohm effective resistance, which you remember is the effective resistance of that 50 plus 10 plus the 40, which we've now put across here? What is the potential difference across here? Well, that is going to be, again, V equals IR. We know what the current is, and we know what the resistance is, so the potential difference is going to be the current, 12 over 55, times the resistance, which is 25. And that's going to equal 5.54 volts. So the potential drop across just that section is 5.54 volts. But remember, there isn't a single resistance here of 25 ohms. As we've constantly said, that is made up of a resistance of 50 ohms, a resistance of 10 ohms, and a resistance of 40 ohms. That's what that 25 ohm resistance really is. And what we're saying is that across that whole thing, there is a potential drop of 5.45 volts. The 10 and the 40 are in parallel to the 50. Remember, the circuit goes like this. So 10 and 40 are in parallel to 50. So there's 5.45 volts across this 50, and there's 5.45 volts across these two resistors, 10 and 40. So what is the resistance across just the 40 ohms? Well, it's going to be 40/50ths of this voltage here, because 5.45 volts goes across the lot. And so the voltage across the 40 ohms is going to be equal to, the voltage across the 40 ohms is going to be 40/50ths or 4/5 of 5.45 volts, which is 4.36 volts. So the voltage going through across the 40 ohm resistor is 4.36 volts. And now we can finally do what we were asked to do, which is to find the current through the 40 ohm resistor. The current through the 40 ohm resistor is the voltage divided by the resistance. The voltage we just found across the 40 ohm resistor is 4.36, divided by the resistance, which is 40, and that will give you a current through the 40 ohm resistor of 0.11 amps. Then the final question, question 12, revolves around alternating current. We are told that there is an alternating current with a frequency of 50 hertz. Its peak voltage is 4 volts. And we're going to use a CRO, a cathode ray oscilloscope, and we're going to have the settings on this that the time base, which is the horizontal value, is going to be set at 4 milliseconds per centimetre, and the voltage base, which is going to be the vertical measurement, is going to be set at 1 volt per centimetre. And you are asked what the shape of the alternating current will look like on the cathode ray oscilloscope. So let's just get the measurements. Each of these is a centimetre on the CRO screen. And along the x-axis, we've been told that that's the time base. So that's 4 milliseconds per centimetre. So every one of those divisions is 4 milliseconds. As far as the vertical is concerned, 1 volt per centimetre. So every one of these is a volt. So we can see that since the peak voltage is 4 volts and it's an alternating current, we're going to get 1, 2, 3, 4. 4 divisions up is going to be where the peak voltage is, and similarly 1, 2, 3, 4. 4 below is where the peak voltage is going to be, because it's going to be an alternating current, so it's going to peak between +4 and -4 volts. But what about the time axis? Well, we know the frequency is 50 hertz, and we know that the period is equal to 1 over f. That is to say, the time for one wavelength is 1 over f, which is 1 over 50, which is 0.02 seconds. And that equals 20 milliseconds. And I told you that the time base was going to be at 4 milliseconds per centimetre. So every one of those is 4 milliseconds, but the complete wavelength will take 20 milliseconds. So we will need 5, 1, 2, 3, 4, 5 for a complete wave. And that's a wave that will look like this. Whoops, it needs to go down to there. And then once again it will need to go up. And 1, 2, 3, 4, 5. It will need to get back to, what am I doing? Down through here and back up there. That's what it's going to look like. I haven't drawn this very well, but you can see what's happened. In the vertical axis, every one of these centimetre divisions represents 1 volt, and the peak voltage is 4 volts. So the alternating current is going to oscillate between plus 4 volts and minus 4 volts. So that's the reason why it goes between these two levels. We calculated the period, that is the length of time for one complete wave, and this is one complete wave. We said that was 20 milliseconds, and since each division is 4 milliseconds, then you'll need 5 divisions for a complete wave. 1, 2, 3, 4, 5. So I've drawn the complete wave to occupy 5 centimetre divisions, and I've tried to do the same thing here, although it looks a little bit odd. So that's the shape that we will get on the cathode ray oscilloscope, which is what we were asked. That for AC. VRMS, the root mean square of voltage, is the maximum voltage divided by the square root of 2. The IRMS, the root mean square current, is the maximum current divided by square root of 2. And in the case of AC, power is equal to the root mean square of the voltage multiplied by the root mean square of the current. Question 1. A battery supplies 5,400 coulombs in 15 minutes. What is the average current? So here we need the formula that I is equal to Q over T. Q is the charge in coulombs, T is the time in seconds. And that is going to be 5,400, because we said it was 5,400 coulombs, divided by 15 minutes. Well, 15 minutes in seconds is 900 seconds, and that gives you a current of 6 amps. Question 2, we are asked to find the drift velocity of electrons flowing through a copper wire, and the information we are given is that copper has 10 to the 29 free electrons per cubic metre. We know that the cross-sectional area of the wire is 6 times 10 to the minus 6 metres. The current flowing through the wire is 10 amps, and the charge on an electron is 1.6 times 10 to the minus 19 coulombs. The formula we're going to need is the one that says that the current is equal to the number of charge carriers times the cross-sectional area times the drift velocity times the charge on each carrier. And that means that V, which is the drift velocity that we need to find, is going to be I divided by NAQ. Well, we know that the current is 10 amps. We know that the number of free electrons is 10 to the 29 per cubic metre. We know that the area is 6 times 10 to the minus 6. And we know that the charge on the electron is 1.6 times 10 to the minus 19. And in circumstances like this, the most difficult thing is to keep track of all the 10 to the minus 6s and 10 to the minus 19s. But if I've got it right, that should be 1.04 times 10 to the minus 4 meters per second. So in fact, the drift velocity of electrons through the copper wire is very, very slow. It is something of the order of 1 millimetre per second. Question 3. We have a 10 volt motor, and we are asked what is the charge that will be required if that motor is to do 100 joules of work. For this we need the formula that voltage is work done divided by the charge, and that gives us that work is equal to the voltage times the charge. and the voltage is 10, and we say that we want 100 joules of work, and we want to know what is the charge, and obviously the charge Q is going to be 10. 10 times 10 is 100. So we need 10 coulombs of charge for a 10 volt motor to be able to do 100 joules worth of work. Now the second part of the question is, suppose that motor engine is only 80% efficient. What charge do you now need? And the answer is that the charge will be the 10 volts divided by 0.8, the 10 coulombs, which was the answer we got here, divided by 0.8 because it's only 80% efficient. And that gives you 12.5 coulombs. You need a higher charge if there's a lower efficiency because some of the work is wasted. That's the whole point about efficiency. If it's less than 100%, you lose energy. And consequently, you needed a high... Hello. Today I'm going to work through a set of questions that you might typically get in an AS level physics exam on electricity. The key formulae that we're going to use is I equals Q over T, that is to say the current is the amount of charge conveyed in a particular time. I equals NAVQ, which tells you about the amount of current depending on the number of charge carriers and their velocity. V equals W over Q, that is the voltage is the work done divided by the charge. R is rho L over A, that's the resistance, is the resistivity times the length divided by the area of a wire. V equals IR, that's Ohm's law. P, the power, is voltage times current. The voltage in a circuit will be the EMF of the battery minus IR, which is the current in the circuit times the internal resistance of the battery. The period of an oscillation is 1 divided by the frequency, and we'll need